In this video, we're going to talk about Taylor and Maclaurin series. Now, I'm actually going to start with this idea of a Maclaurin series to derive where this is coming from, and then we'll talk about Taylor because it's really just recentering where this lives. So we've talked about how we could take polynomials and kind of force them to fit some of these functions that are not polynomials. So we could take a function like ln of x and we could, or 1 over x, and we could rewrite it as a series, as a power series, which is an infinite term of really like an infinite polynomial. And that's where this idea is coming from. So that's where we're going to start. So we're going to derive where this is coming from so that you can find a Taylor polynomial or a Maclaurin polynomial for any function. Because that process of turning it into a geometric function, it can get a little tedious, right? So let's derive it. So derive the Maclaurin polys. So we're going to start with a function that's not a polynomial, because if it's a polynomial, then we already know it's already a nice function. We're not worried about polynomials. We want to turn other things into a sum of terms or string of terms that looks like a polynomial around a certain place. And that's where we're going to talk about that center of that series. So we're going to start with letting f of x be a function that is not a polynomial. So then let's say we could write it as a power series and we were to able to write some of those terms. So the sum from n equals 0 to infinity of a sub n x to the n, if we'll say would represent a function. I'm going to change this then to let. So if I want the nth degree polynomial, it would be a naught plus a1x plus a2x squared plus a3x cubed, and then so on. And if I were to take the derivative of that polynomial, the derivative of a naught, since it is just a number, it's going to be 0. The derivative of the next term would be a1 plus 2a2x plus 3a3x squared plus a whole bunch of other terms, and then it's going to be n a sub n x to the n minus 1. And let's take a second derivative. Now the derivative of a sub 1 is 0, so this is going to be 2a2 plus 3 times 2. When I bring that exponent down, now I'm going to leave it like this so I can think about patterns. A sub 3 x to the first plus dot 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 plus n times n minus 1 times a sub n x to the n minus 2. And let's find a third derivative. We're looking for patterns. So that first term is just going to, the derivative is going to be 2. And this is going to be 3 times 2. Oh, just kidding. Hold on. The derivative of 2a sub 2 is going to be 0. The derivative of the x term is going to be 3 times 2 times a sub 3. And then that last term is going to be n times n minus 1 times a sub n x to the n minus 3. I forgot the n times n minus 1 times n minus 2 when I bring that exponent down, and then I'm going to subtract 1 from the exponent. So that last term is going to be n times n minus 1 times n minus 2 times a sub n x to the n minus 3. And we're looking for patterns here. So if I were to take the nth derivative of this polynomial representation of f of x, you can see what's happening with that last term. That third derivative was just 3 times 2 times a sub 3. The second derivative, that first term was 2 times a sub 2. The first derivative was a sub 1, so it would make sense that that last derivative, the nth derivative, right before I get to 0, would be the coefficients of those exponents, which I could think about as a factorial. It's going to be n times n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 times 1 times a sub n, whatever that was. So we could think about that as n factorial times a sub n. So now we're going to let x be equal to 0. Then what do we have? Now we're going to impose some conditions here. So we want to force f of 0 to equal p of 0 and f prime of 0 to equal p prime of 0, so that that polynomial representation is equal to the function at x equals 0. And we're doing x equals 0 because we're talking about the Maclaurin series, which is centered at 0. So I'm going to write in parentheses that we got to remember that. We got to recall that f and its first derivative, or first n derivatives really, must agree with the values of the polynomial. So we're imposing that condition here. So the nth derivative of 0 over n factorial has to equal a sub n. So what does this mean for us? That means that third derivative of the function over 3 factorial has to equal a3. What that's really saying is that that third derivative evaluated at 0 would have to equal 3 factorial times a sub 3. And then the second derivative at 0 would have to equal 2 factorial times a sub 2, following that pattern that we had up here with the n factorial a sub n being the nth derivative. So that means that the second derivative of the function at 0 over 2 factorial would be equal to whatever that coefficient would be right here. So we've talked about those two, so let's talk about this guy. So that first derivative of 0 would have to equal, looking at that first one, would have to equal 1 times a sub 1, or 1 factorial, which means f prime of 0 over 1, or 1 factorial, would be equal to a sub 1. So if we can see that pattern happening here, then we can derive what's going to happen with a sub n. So what do we have? Well, let's go back to our original polynomial. We had Pn of x. I'm going to copy. So we started out saying we could write that polynomial as an a naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed, and so on. And then we looked at derivatives to figure out the pattern. How can I write those coefficients in front of the x's? So we came up with a pattern for that, looking at just a few of those. Now let's make our substitutions. So A1 would be equal to f prime of 0 over 1 factorial times x. A2 would be equal to f double prime of 0 over 2 factorial times x squared. A3 would be f triple prime of 0 over 3 factorial times x cubed. And then a sub n is going to be f to the nth derivative of 0 over n factorial times x to the n. So I've replaced those coefficients with their representation. We just got to figure out what a naught was. And if we think back to here, if we were forcing the function at 0 to be the same as that polynomial value of 0, then it would have to be what f of 0 is. So that's where our Maclaurin polynomial is coming from. Now, if we want it to be centered somewhere else, this is going to be centered at x equals 0, but let's say we want to force it to go somewhere else. Let's say we want to center at x equals c. Then we're going to do a replacement. We're going to replace x with x minus c, thinking about transformations, and that's going to shift this thing over, and that gives us the Taylor polynomial. So p sub n of x is going to be equal to f of c plus f prime of c, because we're looking at x equals c now, not x equals 0. I'm replacing this x with x minus c plus f double prime of c over 2 factorial. I'm going to replace that x with x minus c. And then f triple prime of c over 3 factorial times x minus c cubed. I'm just going to keep doing that to the nth derivative, replacing that 0 with c. This is going to be x minus c to the nth. So that's where these guys are coming from. Looking at what's happening when we're centered at the books using A instead of C, but you can see how those coefficients are coming out. That's the derivation of it. The only difference between Taylor and Maclaurin is always centered at 0 and Taylor is not. So if I plug in a 0 in here, I'm just going to get just an x out. That would be an x and then an x squared and x cubed and so on in front of those coefficients. So let's go through that derivation with an example. Let's consider the function f of x equals e to the x. So e to the x is not a polynomial function. Our goal is to model a polynomial function that's centered around x equals 0. What that means is when we graph e to the x, that exponential function, around x equals 0, this graph is really going to kind of hug that exponential function, and it's going to veer off on the ends. Okay, when it's centered around a value, like centered around 0, that polynomial is going to hug whatever that non-polynomial function is. So let's start with a linear function. Let's just build a linear model. So we're going through the derivation process here. I'm not using the formulas. This is what the derivation would look like. So I'm going to call this P1 because it's going to be a first degree polynomial. And it's going to look like A naught plus A1x. If I take the derivative of that, it's just going to be A naught. Now I'm looking at the function f of x equals e to the x. I'm centering this around x equals 0. So if I plug 0 in there, I'm going to get e to the 0, which is 1. Okay, I'm forcing this condition. I'm forcing this linear function to look like that exponential at 0. So that's why I'm plugging that 0 in. And then I'm going to plug in, I'm going to look at that derivative, f prime of x. Well, the derivative of e to the x is e to the x. And if I were to look at what's happening at 0, I'm going to get e to the 0 out again, which is 1. So now I'm going to compare. We want to figure out what a naught and what a1 would be. So we want e1 of x to equal f of x. And we're really interested at what's happening at 0, so I'm replacing that x with 0 because I'm centering this at 0. That's why I chose 0. And we want the derivative of p1 of x to equal f prime of x. So we're replacing that x with 0 because we're centered at 0. So let's plug in what we know. I know that at 0, my function, when x equals 0, the output f of 0 is 1. So if I plug this in, I'm going to have a naught plus a1 times 0, and that's got to equal 1. So that means a naught has to be equal to 1. And then if I were to look at that second condition, p prime of 1 at 0 has to equal f prime of 0. So p prime of 1 has to equal a naught. So a naught would be equal to that derivative at 1, which would be f prime of 1, which is equal to 1. So you see how we're getting out a 1 for a1 and for a naught. I made a slight error. Let's go back here. When I take the derivative of p1, the derivative of a naught is 0. The derivative of a1x is just going to be a1. So this guy would actually be equal to a1. Because we know f prime of 0 is going to be equal to that, p prime of 1, and we got 1 for that. So now I know I had that system of equations, two equations, two unknowns, that gave me what the unknown values were. So that polynomial is going to be p1 of x is equal to, we said, a naught plus a1 of x. A naught was 1. A1 is 1. So this is going to be equal to 1 plus x. So if I were to compare this with e to the x, let's look at that graph. So I'm going to open Desmos. So here's my exponential function, and you can see that at x equals 0, that linear function is really hugging that graph. But the linear function stays linear. See how it's veering away from the graph? When I move away from x equals 1 on the left and on the right, we can come up with a better model. The linear function is not a good fit for that. So let's look at a second degree polynomial. we're going to find a second degree polynomial. So what would a second degree polynomial look like? I'll call a piece of 2. It's going to be a naught plus a1x plus a2x squared. So if I take derivatives, the first derivative of that is going to be a sub 1 plus 2a sub 2x. And the second derivative is going to be 2a sub 2. So let's compare that to the original function. My function was f of x equals e to the x. That's what I'm trying to model, that non-polynomial function. The first derivative of that happens to be e to the x, and the second derivative happens to be e to the x also. We're going to force it to look like a polynomial. F of x is going to equal that polynomial at x equals 0, because again, we're centered around 0. So let's figure out what happens when I plug in 0. When I plug 0 into the original function e to the x, I'm going to get 1. When I plug 0 into the derivative, I'm going to get 1. And when I plug 0 into the second derivative, I'm going to get 1. So what do we want to happen? We want the second derivative at 0 to equal f double prime of 0. We want the first derivative at 0 to equal f prime of 0. And we want the original function at 0 to equal f of 0. That's going to give me some equations. So if I plug 0 in for that second derivative, I get 2a sub 2, right? Because that's what it's equal to. And I know the value has to be equal to 0 because that's what we found over here on the other side. So that's going to be equal to 0. I know that my first derivative was a sub 1 plus 2a sub 2 times x. And x is going to be 0. So a sub 1 plus 2a sub 2 times x. And we know that's got to be equal to 1. So I know a sub 1 is going to be equal to 1. And I know a sub 2 is going to be equal to, I don't know why we're at 0 there when that value is 1. That's going to be a 1/2. A sub 2 is 1/2. And then let's look at comparing that other one. Let me go with a purple. So p sub 2 at 0. When I plug 0 in, I'm going to get a naught plus a1 times 0 plus a2 times 0 squared. And that's got to be equal to 1. So that tells me a naught has to be equal to 1. So I know what those coefficients look like now. It took 3 equations to figure out the 3 unknowns. So my polynomial p2 of x would be equal to a naught, which is 1, plus a sub 1, which is 1 times x, plus a sub 2 times x squared, which is 1/2 x squared. So this guy should be a better model than what the other one was. So let's look on Desmond. So if I graph that quadratic we came up with on top of that linear function and that exponential function, you can see how that quadratic is modeling that exponential function a lot better than what that linear function was. I'm going to take the linear function off, see how it's doing a better job of writing that graph. But we could even do better if we did like a fourth order polynomial. Let's do that one just for fun. Let's do a fourth order. So a fourth order polynomial would be a naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth. So that first derivative would be a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus 4a sub 4x cubed. The second derivative would be 2a sub 2 plus 3 times 2 times a sub 3x plus 4 times 3 times a sub 4x squared, which would really be 2a sub 2 plus 6 a sub 3x plus 12 a sub 4x squared. And the third derivative would be 6a sub 3 plus 12 times 2, which is 24. I'll just go ahead and write the 24 a sub 4x. And then the fourth degree, I'm going to use Roman numerals for that one. You see that occasionally, would be 24 a sub 4. Now we're going to force some conditions to happen, right? Because we want this polynomial to model what's going on with f of x, which is a transcendental function at x equals 0. So I'm going to look at the value of the original function e to the x, and then the first derivative, and the second derivative, and the third derivative, and the fourth derivative, all at x. So if I plug in 0 in the original function, e to the 0 is 1. If I plug 0 into the derivative, which is e to the x, I get 1. If I plug 0 into the second derivative, and the third derivative, and the fourth derivative, I'm going to get 1 for all of them. So this is enough to build my system of equations. So I'm going to start with that fourth derivative. I want the fourth derivative of the polynomial to equal the function value of the fourth derivative at 0. So I'm going to replace those x's with 0 there. So that fourth derivative had a value of 24a4, a sub 4. And we know that that value was equal to 1. So a sub 4 has to equal 1 over 24. The value of the third derivative of that fourth degree polynomial has to equal the actual value of the transcendental function at 0. So let's compare those. Comparing these guys. So fourth derivative of the polynomial was 6a sub 3 plus 24a sub 4x, but x was 0, right? Because we're interested in what happens at 0, and that has to be equal to 1. So that means that a sub 3 has to equal 1 over 6. And then we're going to do the same thing for that second derivative. So I'm going to have that second derivative value at 0 for the polynomial has to equal the second derivative value at 0 of the transcendental function. So I have 2a sub 2 plus 6a sub 3 times 0 plus 12a sub 4 times 0 squared all has to equal 1, which means that 2a sub 2 equals 1, so a sub 2 has to equal 1/2. And then I need to compare those first derivatives. So the first derivative of the fourth order polynomial at 0 has to equal the value of the actual first derivative at 0. So a1 plus 2a2x plus 3a sub 3x squared plus 4a sub 4x cubed has to equal 1. And I'm replacing those x's with zeros. So a sub 1 is equal to 1. And then if I compare p sub 4 at 0 with f of 0, that fourth order polynomial at 0 has to have the same value of f of 0. So we have a naught plus a1 times x, which is 0, plus a2 times x squared, plus a3 times x cubed, plus a4 times x to the fourth. And you can see how a naught is going to be 1 there. So we have all of those numbers to plug into our fourth order polynomial. So our fourth order polynomial, which should be a pretty good fit for this, would be 1 plus 1x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the fourth. So if I were to look at that, that's the purple graph. So my exponential function is this green one, is the red one here, e to the x. We started with the linear model. We said it was all right, but not great. The quadratic was better around x equals 0, but look at this fourth degree polynomial. It really does hug that graph around x equals 0, and it veers off on the edges. You can see it starting to veer off over here on that right-hand side. But you see how good of a fit that is. So the more terms you have, the better fit it's going to be. But this is a pretty tedious process if we were doing this by hand, right? So that's where using that derivation is going to come in handy, where we can just take the derivative of whatever our function is and evaluate it at whatever the center is. You can see how those coefficients came out in that denominator. 2 factorial is 2 times 1. Let me scroll back down here. So there's our 2 factorial. 3 factorial is 3 times 2 times 1, which is 6. And 4 factorial is 4 times 3 times 2 times 1, which is 24. So you can see how that's coming out there. So let's look at a few more examples where we're going to find some Maclaurin and Taylor polynomials. We already found it for each of the x. Let's look at sine of x and cosine of x, but instead of deriving it this time, we're just going to jump in and use the formulas for it. So at the top, I've rewritten what my Taylor series would look like. So, and then if we were looking at Maclaurin, we're replacing a with 0 always. So we've got those formulas on this page. Now let's look at what's happening. And like I said, we're going to start with B, looking at sine of x. So we are going to find Maclaurin polynomial is P naught, P or P sub 0, P1, P2, and P3 for each of these. So if I'm looking at P0, P0 would be just f of 0, which is going to be the sine of 0, and we know the sine of 0 is 0. If I'm looking at P1, it's going to be f of 0 plus f prime of 0 times x to the first. So over to the side, I'm going to look at f of x and its derivatives. So there's sine of x. The derivative of sine is cosine of x. And if I plug in 0, I'm going to have sine of 0 plus cosine of 0 times x for this polynomial. Sine of 0 is 0. cosine of 0 is 1. So this is going to be 1 times x, which is just going to be the function y equals x. If I want to find P2 using our formula is going to be f naught, sorry, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. So we're going to need to evaluate the second derivative. I'm going to do that off to the side. So we started with sine of x, derivative of sine is cosine of x, derivative of cosine is negative sine of x. So if I plug everything in, I'm looking at f of 0, which is going to be the sine of 0, plus the derivative, which is cosine of 0, times x, plus negative sine of 0 over 2 factorial times x squared. Now we're going to simplify it. Sine of 0 is 0, cosine of 0 is 1, and sine of 0 is 0. So we're still just going to get the function y equals x. I'm going to box in my answers here. So, and we know what sine of function looks like, and we know what y equals x looks like. So you can see that's not really going to be a good fit for that right now. P of 0 equals 0. Let me box that one in too. So let's find P3. So P3 is going to be f naught, f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial. So we need the third derivative. The derivative of negative sine is going to be cosine. Negative cosine. So we're plugging 0 in. So f of 0 is really finding the sine of 0. F prime of 0 times x would be finding cosine of 0 times x. F double prime would be of 0 over 2 factorial times x squared is negative sine of 0 over 2 factorial times x squared. And then the triple prime is negative cosine of 0 over 3 factorial times x cubed. So let's simplify this. We know sine of 0 is 0. Cosine of 0 is 1. So this is going to be x minus 1 over 3 factorial, which is 1 over 6 times x cubed. So there's our P3. So if I look at our graph, we started with y equals sine of x, which is that guy. We're concerned about what's happening at x equals 0. So when we found that 0-degree polynomial, it's just a horizontal line, y equals 0. When we looked at that first degree polynomial, we got y equals x. The second degree polynomial for this one happened to be the same thing, so that still wasn't a good fit. It's really good at 0, but that's about it. So then what happens when we look at that third degree? Now we've got something that's a pretty good fit right around x equals 0. And if we were to find the fourth degree polynomial, it would look just like this. And that has to do with the way that we're bouncing back and forth between sines and cosines. So you can see how I'm always going to have odd polynomials here, because if I really look at that fourth one, that fourth derivative would go back to sine. And when I look at what's happening at sine of 0 is going to be 0, which means I'm not going to have a coefficient in front of that x to the fourth. I'm going to have 0 times x to the fourth, which would just give me this term back. So let's do that just so you can see what's happening here. So if I look at that fourth one, I'll call it the derivative of the negative cosine. It's going to be the positive sine. So that fourth degree polynomial, I'll call it p sub 4, would be f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed. And then the fourth derivative over 4 factorial of x to the fourth. So this would be sine of 0 plus cosine of 0 times x minus sine of 0 over 2 factorial x squared minus cosine of 0 over 3 factorial x cubed plus, and now we're back to sine of 0 over 4 factorial x to the fourth. Sine of 0, 0, those cancel, and we're left with cosine of 0, which is 1 times x minus x cubed over 3 factorial, which is 6 again. But if we were to look at P5, which needs that fifth derivative, so we're going to find that fifth derivative. Derivative of sine is cosine. So that fifth expansion would look like this, taking derivatives up through that fifth derivative. And anything with a cosine of 0 is going to give us a 1, but sine of 0 terms are still going to cancel out. So we're going to be left with x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. So you can see a pattern emerging here. So this pattern, if I want to figure out what the odd terms are going to look like, P sub, I'll call it 2m plus 1 polynomial, is going to be the sum, and k equals 0 to m, of negative 1 to the k, because the signs are alternating. And that has to do with how the signs of the derivatives are alternating. And it's going to have that same highest exponent as what this subscript would be. And p to the fifth had a fifth degree polynomial. So it would be negative 1 to the k times x to the 2k plus 1 over 2k plus 1 factorial. So we can start seeing patterns on how we can write Taylor or Maclaurin polynomials for transcendental functions. And sometimes we'll be able to come up with some kind of a really concise way of writing that, like we could do for the sine function. So if we go through cosine the same way, I'm just going to go ahead and take derivatives on the side. Derivative of the cosine is negative sine. Second derivative is negative cosine. Third derivative is sine. Fourth derivative is cosine. And fifth derivative would be negative sine. And then if we plug in 0, f of 0 is going to be 1. The first derivative at 0 is 0. Second derivative at 0 is negative 1. Third derivative at 0 is 0, fourth derivative at 0 is 1, and fifth derivative at 0 is 0. So if I want to find P naught, that's just going to be what F naught is for the Maclaurin series, which is just going to be that first term. Was the function at 0, or for cosine, it's going to be 1. If I want the first term, the first P1, the first degree polynomial, is going to be f naught, f of 0 plus f prime of 0 times x. And if I plug in my values, I'm just going to get 1 plus 0x, which is 1. Notice these are the same. So this is going to have a similar outcome to what happened with sine. Because these derivatives bounce back and forth and we get 0 for some of those, it's going to take some of those coefficients out. That P2 ends up being 1 minus x squared over 2. P3 ends up being the same thing. P4 ends up being 1 minus x squared over 2 plus x to the fourth over 24. And P to the fifth is the same thing. So you can see these are coming out with even exponents. Even that 1 we could write as 1 times x to the 0, which would be an even exponent. So we could write that as a sum from n equals 0 to infinity of -1 to the k. So you can see how it's alternating between positives and negatives. And then it's going to be x to the 2k, because we want evens, divided by 2k factorial. So sometimes, like I say, you can see those patterns coming out.